Part 2, and I've got a darker pencil here so we can see what we're doing a bit better. CSU example beam. We're going to be referencing AS 1720.1. That's the timber code. And we're also referencing AS 1170 for loading. Okay. And as I said before, we've got a dead load is 0.5 kPa, and that's from our ceiling, our roof sheets, that kind of thing. We've got a wind load is 1.3 kPa upwards, obviously the dead load's downwards, and the snow is 1.25 kPa, and it's also obviously downward direction. Now we want to work out the loads on the member, and we know that these beams are 900 mil apart. So we'll change this to loads on member times 0.9 times 0.9. So that's the load width on each one, and that becomes 0.45 kilonewtons per meter now. Wind is 1.3 times 0.9 is 1.17 kilonewtons per meter, and snow load 1.25 times 0.9 meters is 1.125 kilonewtons per meter. So that's changed from the load areas, or the pressure, to the load per meter on this beam. Now we'll look at our load cases. Our load case 1 is 1.35 times the dead load. Okay, so that's going to be, we're going to find the moment for that. So 1.35 times 0.45 equals 0.6075 kilonewtons per meter. And if we work out the moment for that, is WL squared on 8, M equals WL squared on 8, that's your basic statics. And that's going to be 0.6075 times L squared. It's a 6 meter beam, so there's a 6 squared over 8, and that comes out to 2.73. So we'll call that M1, 2.73 kilonewton meters. So that is one of our limit states. Okay, I don't know if that yet is the worst case. We can probably see it's if not, which we'll prove in a second. Let's have a look at our 1.2 times the dead load plus 1.5 times the snow load. If we're taking the snow as not an ultimate load already, and that is going to be 1.2 times the dead load, 0.45, plus 1.5 times the snow load of 1.125, and that equals 2.22 kilonewtons per meter. So that is a factored load on the beam. And for our moment, this is going to be an M star equals again WL squared on 8, which equals 2.22 times 6 squared over 8, which is 10.02 kilonewton meters. So M2 is 10.02 kilonewton meters. That's the second one of our limit states. So it's pretty obvious, and it was probably always obvious, that the one with the snow load is going to be more severe than the dead load only. So we're going to design for that. Now we could go ahead and work out the upward moment. We're just going to design the downward moment in this case, so the wind load is not going to come into it. So we're going to design for strength, we're going to design for that, and we're also going to design this beam for deflection downwards. So the next thing we want to do then is say, all right, from a deflection point of view, how big does this beam need to be? Because that often drives the design, and then we'll check that for strength. Now we've got a 6 meter beam. Actually, you recall that, I don't need to draw again. There's a 6 meter beam. And if we said, all right, we took a deflection limit of, it's a roof beam, it's not that critical. If we took a deflection limit of about 60 millimeters, how big would our beam have to be? Now at this point we have to make a couple of decisions. So I'll go ahead and make them for you. Let's use an F11 seasoned beam. We could use glue lamp if we wanted, we could use other things, but we're going to pick an F11 beam. It's a relatively easy type of timber to get, and we're going to go for seasoned. And that makes a difference because when it's seasoned, it's already dried out. If you use unseasoned timber, a lot more deflection happens, that kind of thing. Obviously, seasoned timber is a bit more expensive, but let's go ahead with that. Now, we know also from statics that our deflection is 5 on 384 WL to the power of 4 over EI. Alright? You can look that equation up if you want. That's a basic equation for the deflection of a beam, of a simply supported beam, under continuous load. So just to check our assumptions again, that says the beam is 6 meters. We're neglecting any helpful effects from the cantilevers there, and it's under continuously distributed load. It's not a point load. It doesn't vary, so it's even. So we're taking a few assumptions here. We're also saying that's like a pin support at those points there. So that's a reasonable estimation of our deflection. And right, so we need to find out the W. All right, we're going to take the W under the dead load and the full snow load. So if we take the W as the dead load, which was 0.45, plus the snow load, which was 1.125. And we work out that 1.125 and 0.45. Add those together, we get 1.575 kilonewtons per meter. Okay, that's our load that we're going to work out the deflection for. And we want a deflection of 60 millimeters, a limit of 60 millimeters. Alright, we know our L is 6,000 millimeters. It's worth pointing out that this equation works if you're working in millimeters and newtons. So we've got to translate our kilonewtons into newtons and our meters into millimeters. So that's why we get L is 6,000. Our E is for F11 timber. If we go to the appendix and we find that table, I think it's an appendix. Here we go. Appendix H, table 2.1, characteristic values for design F grades. Short duration, average modulus of elasticity parallel to the grain. That's what we're using here. And F11, we get a value of 10,500. So E equals 10,500. And we want to work out the I. So we can rewrite that equation as I equals 5 over 384 WL to the power of 4 over E times our deflection. And that's all I've just done is multiply by I to get it there and divide by the deflection to get it there. Alright, so we know all those values. That'll give us the I value we're after. Now, one more thing. In deflection for beams, you will remember that there is a duration factor. So that's over in clause 2.4.1.2, effects on deformation. And if you read through that and have a look at the table here in these graphs, it talks about your load duration factor for creep deformation. That's what this is. Our initial moisture content, if it's below 15%, remember it's seasoned, so that we're not over 25. So if our duration is less than 1 day, we get a value of 1. If it's greater than 1 year, we get a value of 2. And you can interpolate using log forms and that kind of thing. I'm going to simplify it, and I'll take the value of J2. We'll take it as 1.1 for now. Remember, we've got a 5-day duration, so it's a bit more than 1 day, but it's a lot less than 1 year. It's not a linear interpolation. You've either got to follow those graphs or do the log interpolation, but we'll take it as 1.1 for now. Okay, so the 1.1, obviously we're going to get a bit more deflection, so we'll go deflection. So we have to divide our E value by 1.1, because basically it affects by reducing the E value. So we'll come to that. So I equals 5 over 384 times our W, which was 1.575. Oh yeah, kilonewtons per meter is also the same as newtons per millimeter. So 1.575 times 6,000 to the power of 4 over, we'll go E value, which is 10,500 over 1.1 times our deflection. Target deflection was 60 mil. And we get an I value when I put all that in to the calculator now. We get 3, 5, 6, 4, and quite a lot of zeros at the end of it. Now that's our I value. So we have to translate that I value into a size of a member. And we know that I equals BH cubed over 12. Now a typical, a very common size of timber beam is a 45 millimeter wide. For a season beam, starts off as 50, shrinks to 45. So if we put 45 in there, what do we get for that? We get that divided by 45 times 12, and we'll take the cube root of that, and that should give us a rough height. Okay, we end up with a beam, let's say it's 45 times 243. So let's take that 245, which is another common size beam. So we're going to take an F11 beam, 245 millimeters by 45 millimeters. Sorry, 240. We'll take 240 is the common size. If it looks a little bit like I ended up this by magic, yeah, that's true. I did. I calculated this backwards before, but that's the sort of size beam. So what we're going to do now is we're going to check the strength of that beam to see if it does all these loads. Okay. All right. Come back to part 3.